Swayam Prabha. Digital India. Educated India.
I welcome you once again to this course on flow through porous media. We were discussing about continuity and we are discussing about continuity equation, and more specifically we were discussing about complex potential. We were discussing about potential function and stream function and their combination in terms of complex potential. Now we are going to see how we can use complex potential in our study of flow through porous media. So, what we are discussing in the last lecture is that we have already defined what is this stream function and what is this potential function and what is this stream function. So, we said that in a 2D system velocity components can be related to stream function and potential function in the form that is mentioned here. Now, we want to define here something called a complex potential, which is phi plus I psi, where phi and psi they are function of x and y. So, now if this is the complex potential, if we want to take a derivative of it, so we are having x and y. So, that is these are the coordinates x and y. So, now we are writing z as x plus I y. Okay. So, now we are writing fz as we are writing as phi plus I psi. So, now fz, if we want to take a derivative of this fz, so if we take a derivative of this fz, what we get is df. If we take a derivative of a complex number, there is a certain way to take a derivative of complex number. This is available in standard mathematics book, that either you take del phi del x plus I del psi del x, this could be possible, or we can take del psi del y minus I del phi del y. So, it has to be either in terms of x, because here see the argument z itself is x plus I y. So, either you take the derivative with respect to x like this, or you take the derivative with respect to y, but then it becomes del psi del y minus I del phi del x. I am not taking this is available in mathematics book if you take a derivative of a complex number. Now, we can see that this del psi del y, we have already defined del psi del y as u, and del phi del y we have already defined as v. So, we can write these as u minus iv, u minus iv, that is what is f prime z. Now, u minus iv, we define this u minus iv as complex velocity, and we give this reference wz. So, this is the complex potential, and I mean see it is something like this. And now, earlier we had a potential which is phi, and we had taken a derivative of it and we got the velocity. We have taken a derivative in y direction, we got the y component of the velocity. Now, we are calling it a complex potential, and we are it is basically consisting. So, the real part is only phi only. So, when we take a derivative of it, just by the same token we should get velocity. So, when we take a derivative of this complex potential, we get, instead of a real velocity as we had it here, we get a complex velocity, and this complex velocity is referred here as w as a function of z. So, now with this understanding of complex potential, what we are going to do is we are going to look at some elemental flows. What are these elemental flows? Let us say we work with some of the unit complex potentials. Let us say some examples. One is Fz is equal to Uz. Later on we will take different forms of this fz. So, fz is equal to uz. Okay. So, then what would be wz? Wz would be the derivative of it, and wz we have already seen that in the last session, in the last slide we have seen that w is basically u minus iv. W is u minus iv and w is df dz. If w is df dz and w is u minus iv, so here we can write w as u minus iv, and these, when we take a derivative of these with respect to z, we get u. So, df dz is u. So, wz is u minus iv, and on the other hand if we take the derivative it is capital U. So, what that means is that for this type of flow here, u is equal to capital U and v is equal to 0, right, because on the right hand side I have only the real component, u is some constant, let us say u is some constant number. So, then we have we can see if we match real with real, imaginary with imaginary, I see real is basically capital U and imaginary is, there is no imaginary component here, it is 0. Okay. So, when you took the derivative it is u, derivative uz is u, with respect to z it is u, and this u is u minus iv, it has to be. So, then what you get is u, small u is equal to capital U and this v is equal to 0. So, what kind of flow we are talking about? We are talking about a velocity field which is u I hat plus 0 j hat. So, that means it is the velocity in x direction. So, if somebody plots this versus, let us say this is x and this is y. So, we are talking about velocity, this is the type of velocity we are looking at, okay, and the velocity is u and we are talking about velocity in x direction. So, if z is equal to uz is an elemental flow which is the flow in x direction at uniform velocity capital U. Now, we look at the velocity fz, this elemental flow. What we are trying to do is we are trying to find out different expressions for fz, where fz represents some elemental flows. So, fz equal to minus ivz. So, in that case if we take the derivative of it, it becomes minus iv, and on the other hand wz is u minus iv. So, if we equate the two, here in this case we see u is equal to 0 and v is equal to capital V. So, what kind of flow we are taking, flow is taking place here? Here in this case, the flow is basically, the velocity is 0 I hat plus v j hat, and the velocity and the fluid flow that we are talking about is velocity in y direction, uniform with the value v. So, this is the next elemental flow which is the flow in y direction. Next is we are looking at fz equal to c e to the power minus I alpha into z. So, this is another elemental flow. Now, if we take the derivative of if we take the derivative of this expression fz equal to this quantity c e to the power minus I alpha z, if we take the derivative, what we end up seeing is that it would be see e to the power I theta, e to the power I theta is equal to cos theta plus I sin theta, right. E to the power c e to the power minus I alpha z. So, when we take the derivative with respect to z, it would be c e to the power minus I alpha. So, you can write this as c e to the power minus I alpha can be written as c cos alpha minus I c sin alpha. So, this is what is happening here, as Wz is equal to u minus iv, which is equal to c cos alpha plus minus ic sin alpha. So, what that means is, then in this case it has to be u minus iv. So, u is equal to c cos alpha and v is equal to c sin alpha. So, if that has to happen, so that means this is talking about a velocity with magnitude c at an angle alpha to x axis. So, we are looking at velocity neither in x direction nor in y direction, but velocity at an angle alpha, to x axis. So, uniform velocity. So, this is referred as Fz is equal to c e to the power minus I alpha into z. Similarly, you can have Fz, the elemental flow, which is equal to c ln z. C ln z can be written as c ln, now z is equal to x plus I y. So, x plus I y, if you forget about the xy system, if we forget about the xy system and work with the r theta system, so in that case any point on this, with let us say at distance, radial distance r and this angle theta, so then we can write this x component as x equal to r cos theta and the y component would be r 90 degree minus cos 90 degree minus theta or r sin theta. So, y component is r sin theta. So, that means z is equal to x plus I y. If we want to shift from Cartesian system to the other cylindrical system or r theta system, then you can write this as r cos theta plus I r sin theta. So, if you take r common, you write these as cos theta plus I sin theta. So, you can write these as equal to r e to the power I theta. This is we have used these already in this context before. This is Euler's formula, that cos theta plus I sin theta can be written as e to the power I theta. So, it is r e to the power I theta. So, instead of c ln z, we can write c ln, and instead of z we can write r e to the power I theta. So, first of all, these are of one types of flow. These first three that we are discussing, u z minus I v z and this quantity c e to the power minus I alpha z. These we have already mentioned. One is horizontal flow, another is vertical flow, another is flow at an angle. So, these three are of one particular type, but C ln z is a new type. So, C ln z, first of all, what kind of flow we are looking at. So, to find this, instead of finding out the velocity, let us first look at how the potential function and stream function, how, or potential lines and stream lines, how do they look. So, we see here that f z is equal to C ln z. So, f z is equal to C ln z leads to C ln r e to the power I theta, and if we break it up, it becomes C ln r and C ln of e to the power I theta. So, ln of e to the power I theta would be simply I theta. Ln of e to the power I theta, that would be simply equal to I theta. So, C ln e to the, so ln of a into b, that is ln a plus ln b. So, ln a is ln r and ln b is I theta. So, it is C ln r plus I c theta. Why we are doing this? Because we can see here, this is the real component C ln r and c theta is the imaginary component, and we know that our original definition of Fz was phi plus I psi. Phi plus I psi, that was the definition of Fz. So, then in that case the real component is basically the phi and the imaginary component is basically the psi. So, we are talking about now, we are talking about stream function phi is equal to C ln R, and potential function we have this we have the potential function which is C ln R, and the stream function which is equal to C theta. So, what is potential function? Potential function or what is potential lines? Potential lines are the lines along which potential function is constant, and stream function, streamlines are the lines along which stream function is constant. So, I am looking at lines along which stream function is constant. So, or in other words, I am looking at lines along which C theta is constant. So, what would be this line in this context? What would be this line? What would be this line in this context where the C theta will be constant? So, we are talking about some line along which theta is constant. C is some arbitrary constant. So, we are looking at some line along which theta is constant. What is that line in a r theta system along which theta is constant? See, in r theta system we can have, if this is the point, this is the center, we can have these lines radially outward, or we can have these lines which are circles in r theta system. So, the line along which the stream function is constant are the lines along which theta is constant. I see that the theta, as far as this line is concerned, this is the theta. So, wherever you go, this theta remains same. So, I can say that this is a line along which theta remains constant. This is also another line along which theta remains constant. So, we can say that these are the lines along which C theta remains constant. It is maybe C theta 1, this may be C theta 2, this may be C theta 3, but these are the lines along which these are constant. So, I can say these are the lines along which the psi is constant. Maybe I call this psi is equal to psi 1, this is psi is equal to psi 2, this is psi is equal to psi 3. So, along these lines the psi would be constant. So, these are then the streamlines. So, what kind of flow we are talking about, where these are the radial lines coming out from a point and these lines are the streamlines. So, naturally we are talking about a source. And what are the potential lines in this case? Potential lines are the lines along which the potential function remains constant. So, that means the C ln R remains constant. C ln R, anyway C is a constant. So, the lines along which R remains constant. So, line along which R remains constant in this setup is, this is one line, this circle around this center, this has R as constant, some fixed R is there. Then this next line where the R is constant, some other R, it is R1, this is R2, that is R3. So, this is, so I can say this line has C ln R1 is constant, this line has C ln R2 as constant, this line has C ln R3 as constant, or in other words, I can say that this is the line along which the potential function phi is constant, and let us say this is phi 1, this is phi 2, and we can draw another line which is phi 3. So, the potential lines are the circles, and they make perfect sense because the radius is perpendicular to the the circle, the radius is perpendicular to this line, to these circles. So these circles are the potential lines, and the radial lines coming out from that point, these are the streamlines. So you can see that when we talk about Fz, this Fz as C ln z, we are talking about a source, elemental flow of a source. It may not have to be source alone, it can also be sink, depending on the sign of C. C can be negative. If C is positive, it is a source, I agree, but if C is negative, in that case we have to talk about a sink there. So that means the flow, the streamlines would be inward. Streamlines, instead of coming out from a point, emerging out from a point, they will be directed towards a point. So then it will act as a sink. The next one that we have here is another elemental flow, which is Fz equal to I minus IC ln z. Instead of C ln z, now we put this as an imaginary component. Instead of real, we are putting it as imaginary. The C ln z is put as an imaginary component. So then we do the same exercise here. Instead of ln z, we are writing ln r of e to the power I theta. So r e to the power I theta means this z is equal to r e to the power I theta. We have already seen this. Z is x plus I y, and x is r cos theta for this system, y is r sin theta for this system. For r theta, when we convert from Cartesian to r theta system, and then we said r we have taken out common, which is then making it cos theta plus I sin theta, and then we said that it is then further r cos theta plus I sin theta can be using Euler's theorem, we can write it as r e to the power I theta. So the same thing applies here. Instead of I c ln z minus I c ln z, we are writing minus I c ln r e to the power minus I theta. Then you break it, ln of a into b is ln a plus ln b. So it would be minus I c ln r minus I c ln e to the power I theta, and ln e to the power I theta is simply I theta, as we have seen. So if we break this up, we get c theta minus I c ln r. If we go to the next step. So now again we are writing this Fz as we had done earlier. Fz we are writing as phi plus I psi. So then we have this c theta as phi and minus c ln r as psi, and c theta as phi. So in this case we are talking about stream function psi is equal to c ln r. So that means streamlines are the lines along which stream function is constant. So that means streamlines are the lines along which c ln r would be constant, or in other words, streamlines are the lines along which r is constant. Whereas in case of potential lines, along which the potential function is constant, or in other words, potential lines are the lines along which theta is constant. So I think it is just the opposite of what we have seen earlier in C ln z. In case of C ln z, we saw streamlines are the lines that are coming out. Streamlines are the lines that are coming out, but this time we see that the streamlines are the lines. We see that the streamlines are the lines along which the r is constant. So that means this is the new streamline. This is the new streamline. This is the new streamline. So these are the streamlines now, not potential lines. And what are the potential lines? Potential lines are the lines along which theta is constant. So that means these are now the new potential lines. So the streamlines are these lines now, the circles. So what kind of flow we are talking about? Where streamlines are circles, we are talking about the flow of vortex. So of course, when it comes to vortex, and people generally talk about free vortex or forced vortex. We are referring to free vortex. there is no viscosity involved here, no layer is sliding against the other. Generally, whenever there is a vortex at the near the core of the vortex, it is called forced vortex, and there viscosity plays a role, but away from the center of the vortex one can get a free vortex where the flow is in circular streamlines. So, we are referring to free vortex. So, this is a vortex. So, essentially this equation, the Fz equal to C ln z is basically source or sink, and this is vortex. To be vortex is good enough, but if you are a little fussy about it, let us call this free vortex. So, these are the elemental flows. First three were three types of, one is horizontal, the other is vertical, another is at an angle. So, these are that kind of velocity, whereas this C ln z, this is the first time we saw that it is basically source or sink, and this one here minus I C ln z, here we see this is the equation for a vortex. So, these are the elemental flows. What we are going to do next is we will use these elemental flows to come up with, see the advantage of working with these elemental flows is if the two flows are superposed, that means I have a source, I have a source where I have the flow is coming out, let us say I have a well, something is producing, I have another well nearby where it is acting as a sink, and then I have some line source available on the side. So, if you have a situation like this and if you want to plot the streamlines, if you want to see where the streamlines are coming close to each other or they are diverging, that means where the velocity is more and where the velocity is less, what you will do is simply take the elemental flow of a source, elemental flow of a sink, so different types of elemental flows and simply superpose them. That means f of z of source plus f of, so you just simply add them and find out what is the net phi, what is the net psi, and net psi gives you the streamline, and based on this net phi and net psi you can find out what are the velocities for in Cartesian or cylindrical. So, that is the advantage of getting into this exercise of complex potential. I will continue with this exercise of superposing these elemental flows in my next lecture. So, better you do some revision of these concepts before we get into the next lecture, and this is all I have for today for this lecture. Let's meet again in the next class where we start playing with these superposed situations of these elemental flows. That is all I have for this lecture. Thank you very much.